We're going to look at two more functions where we determine the character of the zeros, and then we find the zeros and graph the functions. Here's problem number 5. F of x is equal to x minus 3 squared plus 2. Okay, so to find the zeros, we just set this function equal to 0. And then we move this 2 to the other side. And we can see that we have something being squared is equal to a negative 2. Because we can't square a real number and get a negative, that tells us that we have two complex zeros. And we also know that because we have complex zeros, the graph of this function doesn't go through the x-axis. Now we can graph this pretty quickly because this is in the form a times x minus h squared plus k. Here you can see that the vertex, which is h comma k, is equal to 3 comma 2. So let's go ahead and put a point at 3, 2 right here. We see that the a is 1, and that means the graph is pointing upwards. And we don't make this graph any skinnier or wider because a is 1. So it's just the normal parent function, x squared. But what do we do to the parent function? We move it to the right 3 and then up 2. That's exactly what we have here. So the parent function also goes through these points here. So this is the parent function, x squared. So if it goes through these 2 points, then they also have to be moved to the right 3 and up 2. So this function f of x looks like this. So something like that. And again, how we know how to graph this is we look at this function and compare it to x squared. We know that we have to put inside this function here x minus 3, which corresponds to moving the graph to the right 3. And this plus 2 is on the outside of the function, so we move it up 2. We can also just graph the vertex, determine if the graph is pointing up or down, which we have already. We know it's pointing it up because a is 1, and we find another point on the graph. Now, to find another point on the graph, you can just plug in a number for x. And you can see if you plug in 4 into here, you get 4 minus 3, which is 1. Square it, you get 1. 1 plus 2 is 3. So you have a point at 4, 3. And using the fact that this graph is symmetric, you know that you would have a point over here as well. So that's another way to graph this. All right, so we have graphed the function. Now let's find the zeros of the function. So we've almost finished the part where we need to find the zeros. We just look at this piece here. We have something squared is equal to negative 2. So what we can do is take the square root of both sides. So we get x minus 3 is equal to plus or minus square root negative 2. And the square root of negative 2 is the same thing as the square root of 2 times the square root of negative 1, which is I. So we have x minus 3 is equal to plus or minus square root 2i. Then we move the 3 to the other side. And here are our two complex solutions. I'm going to write them separately. We have 3 plus square root 2i. And remember, the complex conjugate, which you can see right here, is 3 minus square root 2i. So those are our two zeros. Another way to do this problem is you could FOIL this out. If you FOIL this out, you get x squared minus 6x plus 9 plus 2. which is x squared minus 6x plus 11, and you could use the quadratic formula. When you use the quadratic formula, you should get the same roots here. I'm not going to do that because I'm going to use the quadratic for the next function, but that's a good exercise to check and see if you get the same x-intercepts. Okay, so this is the final problem. We have g of x is equal to negative 3x squared plus 6x plus 1. So we want to characterize the zeros of the function here. Now this is in the form g of x is equal to ax squared plus bx plus c. And since this is in this form, if we set it equal to 0, we could try to factor it, but I don't think that this is factorable over the real numbers, because if we put negative 3 here and 6 here, two numbers that multiply to give me negative 3 and add to give me 6, well, 3 just breaks into 3 and 1. So that won't add to give me 6. So it's not, as far as I could see, it's not factorable over the real numbers. So I think we're going to have two complex solutions. Now how we can check that is, remember that the quadratic formula is negative b plus or minus the square root b squared minus 4ac all divided by 2a. And what determines if we have complex roots is this b squared minus 4ac. So what I'm going to do is I'm just going to see if b squared minus 4ac is less than 0. If it's less than 0, then we're going to have two complex roots. If it is equal to 0, then we're just going to have one real root. And if it's greater than 0, we're going to have two real roots. So let's see, b squared minus 4ac is equal to, well, here the b is 6. So this is 36 minus 4. A is negative 3, and c is 1. Okay, 36 minus 4 times a times c. And you can see that I get 36 plus 12, which is 48. So this number is positive, which tells me I'm going to have two real roots. Okay, because I have two real roots, let's go ahead and find what they are. So x is equal to, so remember b is 6, so we get negative 6 plus or minus square root. We've already found this. I believe we said it was 48. Yeah, because it was 36 plus 12. Yes, which was 48. And then we divide this by 2 times a. A is equal to negative 3. So we get negative 6 plus or minus square root 48 over negative 6. Okay, let's simplify the square root 48. That is equal to square root of 4 times the square root of 12, because 4 times 12 is 48. This is a perfect square, so we get 2 root 12. We can simplify the 12 too. This is square root 4 times square root 3. Bring down this 2. So this is also 2. So we get 2 times square root 3, which is 4 square root 3. So we are going to substitute that in right here. I'm going to erase this square root 48, and I'm going to put 4 square root 3. So I get that x is equal to negative 6 plus or minus 4 root 3 divided by negative 6. So notice that each one of these has a 2 in common. Let's get rid of that. So we have x is equal to, you know, what I'm going to do is I'm going to go ahead and separate it. So negative 6 plus 4 root 3 over negative 6. And x is equal to negative 6 minus 4 root 3 over negative 6. That way I can divide everything by 2, and I also want to get rid of this negative because we don't usually put negatives in the denominator. So I'm going to divide everything by a negative as well, which is going to just change all the signs. So I get x is equal to, if we divide by 2, we get 3 minus, divide by 2, 2 root 3 over 3. And this one is x is equal to, it's also going to be a 3 plus 2 root 3 over 3. Notice I also got changed the signs like I mentioned. So these are our two x-intercepts or zeros. We can get an estimate for these. Let's put into a calculator just so I can have an idea of what this is. I'm going to put in 3 minus 2 root 3 over 3 in a calculator. So let me do that. That is about negative 0.15. And the other one is about 2.15. Okay, so if we were to graph this, so this is 1 here, and I said negative 0.15. So if this is a half, it's going to be really close to 0. I'm just going to guess about right there. And then the other one is 2.15. So here's 2, so I'll say about right here. What else can we tell about this function? We see that the a is negative, which tells us we're pointing downwards. We should keep that in mind. Let's find the vertex. That'll give us another point and a good estimate for the graph. So the vertex is negative b over 2a, comma, f of negative b over 2a. So negative b over 2a is equal to negative 6 over 2 times negative 3, which is also negative 6, so we just get 1. And if we plug, sorry, this should be a g because that's what I'm naming my function, so g. If I plug in 1 into this function, I get negative 3 plus 6 plus 1, which is 4. So I get 1, 4 right here. Put that in blue. And then my function is going to look like this. And you should always ask yourself questions like, does this vertex make sense? Because it's really easy to make a mistake when you do a vertex and x-intercepts and stuff. And look, it looks like it's halfway between these two. So to me, the vertex would make sense. And it's above those two x-intercepts, which tells me the graph's pointing downwards, which is true because this is a negative. So just like little things to make sure you're doing something correct. I did want to mention that when we did this problem, we ended up getting 2 real roots. And we've seen problems like this before. And the last problem, we got 2 imaginary roots. And I just want to show you what would happen when you have, when you use the quadratic formula, because I don't think we've seen that. I don't think we've seen using the quadratic formula and getting the roots quite like we did before. So let me just go through that really quickly. Sorry, I'm trying to erase this. Let me try again. So for this last problem, we found the roots by moving that 2 to the other side when we set it equal to 0. And you see we got 3 plus or minus 2i. Let's use the quadratic formula just so that we have another way to view this. Okay, so we set this equal to 0. And then we're going to FOIL this x minus 3 squared and then add 2 to it. So we get x squared minus 3x plus 9 plus 2. So we get 0 is equal to x squared minus 6x plus 11. So this is the general form where a is equal to 1, b is equal to negative 6, and c is equal to 11. Now to find the roots, we say x is equal to negative b, which is 6 here, plus minus square root, I'm using the quadratic formula, b squared minus 4 times 1 times 11, all divided by 2 times 1. Okay, so we're going to simplify this. We get x is equal to 6 plus or minus square root. We have 36 minus, I can write it here, 36 minus 44. Now let's see if we can simplify that. That will be 8, right? 36 minus 44 is negative 8 all over 2. Now, notice that this is a negative number underneath the square root, which tells us we're going to have 2 complex roots. From there, I'm going to break up this square root negative 8. This is the square root of 8 times the square root of negative 1. Again, that is I. And the square root of 8 is 4 times the square root of 2. And that's a perfect square, so we get 2 root 2i. So I can erase this and put 2 root 2i. And now we're going to do something similar to what we did just a minute ago. We can break this into 2 different roots. And then divide everything by 2. Well, if you divide everything by 2, you get 3, and then you get a 1 here. I don't have to put the 1 there because it's just known to be 1. And then here I also get a 3 and a 1. And I believe when we started here, which was a lot easier when we set this equal to 0 and moved the 2 over into the square root, we got the same thing. This was a more complicated way to get it, but I just wanted you to see that you can find the roots using the quadratic formula, and we were able to see right here when we got a negative that we had 2 complex roots. And here you can see they are complex conjugates. So that is it for this section.